Okay, so okay, few terms are not clear to me right now, so I will explain them in the next class. Okay, so after solving the equation, we what we come up with the okay. I'm not going to details because some terms are cancelled are not clear to me. So we end up with this equation here. Okay, this equation here. So I'm taking a look on the final equation. So if you compare this final equation, this is like a left hand side. This is right hand side. Right hand side again is written here after equal to sign. So this term is written in this way. Okay. So what is written here is that 1 upon density and derivative of pressure gradient. And what we have taken here is that you see that this is dynamic, this is kinematic viscosity. Kinematic viscosity is equal to the dynamic viscosity divided by the density. Okay. So, so here, if I take out the 1 upon rho outside, so what will remain there inside is going to be the this mu. Okay, this mu is here. Okay, so from the first term, what we taken out is that 1 upon the density is outside and the first derivative d by dy. So remaining term will be the du by dy. Okay, and viscosity as well. So u, the mu, and du by dy. And this term is actually written as this is the minus u bar, v bar, and the average sign here. Okay, this is actually called the Reynolds stress. Okay, so now if you take a look on the equation completely, this equation this term and this term, they are exactly same as the without averaging. Okay, go back and you will see here that this equation, which is given here, this is the minus 1 upon rho delta p by delta x, and this shares this term here, that these terms, all terms, and this is like a steady state term because steady state equation does not contain the transient term, so this is also removed. But remaining terms, they are exactly same. Only difference is that now that equation contains the one extra term, that is the u bar, v bar, and the average, and also they have the average sign on these values. That's the only difference here. Okay, so we will go back here. So this contains the same thing, and these are the actually average quantity. These all are without the like a bar sign. These are with the average sign. This is the average quantities. Okay, mean velocities, mean pressure terms, and only term that is containing the fluctuating component is over here. And this is what actually called turbulence modeling. Okay, so to find out this thing, actually we have the different methods to find out these values. This is called turbulence modeling. We have the various methods I discussed. One is mixing length model of the Prandtl. Then other models also there. Okay, so our whole theory of turbulence modeling for the RANs or U-RANs revolves around this term. Okay, everything else is solved as normal as we solve for the laminar flow. Okay, momentum equation, continuity equation, all these terms are solved as we solve them for the laminar flow. The only thing that is different is this term. Okay, so now let's put the equation again here, and I'm not putting the bar sign here. Bar sign is for the averaging. Okay, so this is understood. This is average quantities are here. Okay, now this term is we are going to remove because for the flat plate pressure gradient 0. For the flat plate, we are solving that under the zero pressure gradient. This term can be also assumed 0, but this is not true for the every case. Okay, now this term that is actually is over here. We multiply with the density. This term is this term is over here. So this term contains the. Please give me 1 minute. Okay, so this is like a complete Reynolds stress tensor for the these all terms. Okay, so you can see if you want to solve the and this term and this term, they are same. Okay, and this term and this term are same. So totally there are 6 unknowns actually. Okay, and this is when you're solving the non-stress turbulence model, you have to solve the 6 equations. For SA model, you have to solve the 1 equation. For K omega, K omega model, K epsilon model, you solve the 2 equations. 1 equation for the K and 1 equation for the epsilon, or 1 for K and 1 for the omega. Okay. So at the end of day, what we are going to determine is this term here actually. So this term, once you solve the this equation as you normally solve for laminar flow, and then you go for the turbulence model, you solve this equation there, and how to solve this equation I will show you. And then you add the term here and you will get a solution for the momentum equation. Okay, and then you continue loop for the continuum equation, momentum equation. Then again you go for the turbulence modeling and get this term, again put term over here, and then you again continue for the this whole thing again and again. Okay, so how this term is changed to the turbulence model, I will let you know. Okay, so if you go there, so mixing length model is is based on the by the Prandtl, and what he says is that that eddy size, that is a mixing length model. So based on the mixing length model, we can actually approximate that viscosity based on the mixing length. So how they approximated? This derivation is given here. This is from the Wilcox book. So they are saying that the we can find out the this like a pressure term, like that term, this term here. That's the same term which is like a given here without the density. So this is the u bar. Okay, at the different location, this is equal to, this is like a value at the y plus lm minus u bar. This is equal to the u bar, u dash whole bar. Okay, this is equal to the mixing length du by dy. So this is same as this term. Okay, this thing, this thing. Okay, so now this term can be, now this is for the single value, and we are assuming that the u bar dash and the u dash bar is same as the two terms. So this can be written as the actually square of these two terms. Okay, so I can write it down the L mean like a mixing length square into the this derivative square. Okay, so simplify this thing and we end up with this equation in this way. So now what we are trying to do is that we are trying to find out the actually a turbulent viscosity. So turbulent viscosity can be costed in this form. So I can cancel out the one derivative here. And so I will end up with the rho mixing length square du by dy. So the turbulent viscosity is now equal to this term. So this is like a single term that we are going to determine now. Okay. So we found various turbulence models. So we are after this term. And once we get this value, now we can also cause them again back to our original equation. Okay. So now the game is that we have to find out this term. This term is from the a mean equation that is already known to us at that solution step. So we have to find out the mixing length and put the value there, and we will be ending up with the finding out the turbulent viscosity. Okay. So this term is here. So this term can be written as the first equation, second equation. So we have to find out the mu t. This is the laminar shear stress. This is the turbulent shear stress. Okay. So the mu t is equal to this term, and this term is equal to the mu t into du by dy. Simple. Okay. So the thing is that how to find out the mixing length. So mixing length we can find out in the a boundary layer with this formula. In the initial region, this is directly proportional to the both terms x and y. After that, this value will be constant. Okay, this is from the external data that contains these two graphs. So this is from here. Okay, this is the molecular shear stress, and this is the turbulent shear stress. Okay, so the xy over the about the 20% of the boundary layer thickness. So for first 20% of boundary layer thickness, you have to apply the formula that is x into y. So it is a proportional to the both x and y. Okay, it's like at 45 degrees. And after that, this is equal to the delta and the lambda into the delta. So it's this value is equal to the this length scale is equal to the lambda into the delta. Simple thing. Okay. Anything you want to ask?
Sir, your mic is off.
I think your mic is off.
Any questions?
Your
Okay.
mic was off. So
Mic is
that's
on or
that.
off? Now
No,
it's on.
no, it's okay. Now it's okay.
Okay. So when tries they proposed them in the modification in 1952. So there is a, like only one constant here, and everything else is like a dependent on the y plus value. Okay. This is like a, some sort of general model here actually. And and also they have the damping function here, and for the outer wake region they have the formula for like this way. This was proposed by the class in 1956. And also there is another like change that was like proposed by the SQ Dyer 1966, that he said the maximum L like a maximum mix length is limited to the 0.09 R, where R is a half length, half height of the channel or the radius of the cylinder. And then they proposed that the value maximum value of the LM should be limited to the 0.09 of the delta. Okay. One common mixing length is given by this formula. This is more generic form than the like the previous models. And other algebraic models, like we have the CBC Simmons model, that is like a very famous model, like before the invention of the commercial CFD. And Baldwin-Lomax model was like at the moment SST model is like a go for model for every flow. Like 30 years back, like Baldwin Gomez model was the model for the every simulation. Okay. So it's a two-layer model, not two equation model. Two layers means there will be two flows, two layers are there of the flow, one inner layer, second outer layer. And this model was very good for separated flows and with the shock waves. So for the like aerofoils, for the wings and like these ones, these cases, they like use this model very extensively, like 30 to 40 years back. Okay. After that, like in 19 and the for your information, K epsilon model and K omega model. K epsilon model is like a older model, and K omega also. They were also invented in like in 1970s. Okay. But they had the problems. Once they modified them and improved them, there is now they are not the like a go for model for every simulation right now. But at that time, in the back into 70s, Baldwin Lemons model was very famous model. And 1992, the SA model is the Spalett Almaris. There are two people there who invented this model. And but this was like a very famous model. It still is a very famous model for the external aerodynamic flows. Okay. But for the mixing flows, about jet flows, for like these flows, this is not very famous model actually. So and also one equation model actually have the problems with the, because it's only one equation, so they like suffer from the issues like not successful for every flow. So there's a need for the establishment of the two equation models. Okay. So I told you that we can divide the bond layer into the like three layers: the viscous sublayer, buffer layer, and the log layer. Okay. And the log layer is actually like universal in the nature. That's why this is also called the universal logarithm layer. Okay. So I can define the u plus and y plus. So friction velocity is given by this formula, and from the shear stress we can find out shear stress by this formula. And non-dimensional velocity u plus can be defined as a u divided by friction velocity, and non-dimensional wall distance y plus defined by this formula. So actually, the Y plus calculators here that you see on the internet, they based on these two equations. So how to find out the values? What they propose is that friction velocity, you have to find out first friction velocity. And friction velocity, for friction velocity, we need to find out the wall shear stress. So, but the wall shear stress is actually like a CF is equal to coefficient of friction is equal to the wall shear stress divided by 1 upon 2 rho u square. Okay, so from here I can solve for wall shear stress. This is equal to the CF into 1 by 2 rho u square. Okay, and then I can put this value. I can find out the CF. CF I can find out from the like correlations which is given here right now, and they are different for the turbulent flow and for laminar flow. Okay, but because of u plus and y plus they are fully only for turbulent flow, so this is equation for turbulent flow. And here, just what you need is a Reynolds number. Okay, put the Reynolds number value here and you will find the CF value. This is not a, it's like a, because CF value varies on the wall from point to point, but this is a very good approximation actually. So from this point, this value, you can find out the shear stress, wall shear stress, and that value you can put into the equation here and divided by the viscosity and take the square root, you will find the friction velocity. Okay. So once you find out this value, then we can find out the U plus and Y plus very easily. Okay. So for example, if you are aiming for the Y plus is equal to 1. Okay. So what you have to do is that you have to find out the first cell height that will provide you the Y plus is equal to 1. So you have to solve for the Y. This is the first cell height. Okay. So this is like a mesh here. So we have the mesh like this. So in the control volume, the first cell height is actually is not this one, but this is over here. Okay, up to the first node from the wall. So you have to find out the Y for this value. Okay, Y is in the normal direction. So you have to find out the Y value here. So I can solve for the Y value. So Y will be equal to the Y plus into viscosity divided by density and the friction velocity. Now friction velocity we already found from this equation, and this equation requires the wall shear stress that we find out from this value. From this formula. Okay, and CF we found out from this formula. So just need the Reynolds number, find out these values. So now what we need is that we are targeting for Y plus is equal. Let's say targeting Y plus is equal to 1. So put the 1 here. Okay. And friction velocity, we calculated from here, let's say this is equal to the 0.2, and the viscosity, let's say, is equal to the 1, and density is 1000. Okay, I'm just giving examples. So it means that if I put this value in the formula, 1 into 1 divided by 1000 into the 0.2, the first cell height, you can write it down like a delta y1, maybe like this way. Okay. This is equal to the 1 divided by the how much? 200. Okay. So if I divide the 1 by 200, my first cell height should be equal to 0.005 meters. We're talking about the SI system. Okay. So first cell height is, for this example, should be equal to 0.005 meter. If you are targeting the Y plus is equal to 1. Okay. But if you target the Y plus is equal to 10, okay, then you have to put the 10 here, and you will end up with the like 100 on the bottom. 100 into 0.2, this will be the 1 upon 20. So first cell height will be equal to the 0.05 meters. Okay, this is for the Y plus 10. And this is the size when you are targeting the Y plus is equal to 1. Okay, so Y plus 10 will require the mesh size of first cell height of 0.05 meters, and you are targeting Y plus is equal to 1, then the first cell height should be the 0.005. And please keep this thing in mind that because velocity will be varying along this whole dimension, so the friction velocity will not be constant because it's a derivative of the shear stress is equal to this wall shear stress is equal to this is normal shear stress, but at the wall. This is equal to the mu du by dy. And when we talk about the wall shear stress, it means that we are talking at the y is equal to 0. Okay. This is actually a derivative of velocity with respect to the normal component. Okay. So if you go in the different cells, the velocity will be different, and so the velocity gradient. Okay. It means that the friction velocity will not be constant in every cell there. Okay. Every cell will be having the different values. And so will be the variation of your for the given Y plus, the first cell height will also vary. So now question is that what should be the value we should be taking for the first cell height? We should be taking value for the first cell height. That is, if your target is that, strictly target is that Y plus should be less than 1 everywhere, then you should target the value that is going to ensure that the Y plus is less than 1 everywhere. If not, you run the simulation, you find out some values are like a 3 or 4. So you have to reduce the size maybe by the half, maybe by the 1/10. Okay, so then you'll end up with the Y plus value of the 1 or maybe 0.9, 0.8. Okay, but don't go for the very low values of Y plus. Maybe you are going like maybe like a 0.01. That will introduce some more errors there. Some errors because of the round-off error, and some maybe other errors as well. Okay, So it is recommended by the scientists, people in the fluid dynamics, that you should not go for the very low Y plus value. So target for around the 1. Okay. Any questions here for the Y plus treatment here? Any questions? No questions? Anyone? Can you hear me?
Sir, where we can find U plus
Where we can find U plus? Actually, this is not required.
software, meshing software.
The U plus, you cannot find the U plus or Y plus, and the Y plus they are given there, but you cannot directly find out the U plus. Okay. So what you have to do is that you have to find out the wall shear stress from simulation. Okay. So how we can find out the wall shear stress? So there's no need to actually approximate with some correlations here. Okay. So how I can find the wall shear stress? This is laminar flow right now, this example. So let's draw the one line here. Okay. And assuming the flow is like a constant across the circumference. So I'm drawing a one line. So before I draw the one line, I'm going to draw the one isosurface. Okay. So this is going to be like a complete plane. Okay. A complete plane like this one. Okay. So now I will be using the isosurface between what? Between the sphere, sorry, the wall of the pipe and the pipe and this x coordinate 5. Okay. So of what? Of the mesh and the same again at the x coordinate. Okay. So what happens here? Let me show you. This is like, maybe it's a good trick for you. So what happens here is that actually we got the two lines. This is one plane. Okay. This is one plane is here. So now by this plane, what I'm going to do is that I'm going to draw the two lines on the circular cylinder. So iso surface. Let's see, can we create this thing or not here? So wall pipe. Okay. I think we should go for the, yes, iso clip. Okay. So iso clip of this. Okay. I think I'm missing some point here. Let me check again. It's a zone is pipe, but okay. Just give me 1 minute. Just trick that I can create the like otherwise I will like let you know about the different way of putting that thing. Okay. So trick is that I will select the wall pipe. Okay. I will select the mesh and I will select the X coordinate and click on the create. Okay. Now, if you display the X coordinate 7, what will happen is that because this is from the like outer surface circumference, this will create the two lines. Okay. But I need only one line here. So I will go for the create iso clip and then I will click on the mesh. Same thing. This time I will change the like a minimum value to the somehow. This is I on the x coordinate 7. So I will now change them. So slightly moving upward because there are only two parts, the extreme negative side and extreme positive side. If I just change it slightly upward, what will happen? This line will disappear. Okay. So click on create. And if you display like x coordinate number, clip coordinate number 8, you will only get the one line. 1 minute. 1 minute. 1 minute. Sorry, this will be the y. Sorry, this will be the y actually. This will be y direction. Okay. So click on create. Okay, so we are now end up with a one single line. Okay. So now this line I can actually plot the wall shear stress. Okay. So xy plot and wall fluxes and the wall shear stress. Okay. You can directly plot the shear stress also, but their shear stress will also be a wall shear stress. Okay. That's along the z direction. And click y coordinate number 9 and plot. Okay. Okay. So values are actually varying here. Different values are different location, different values are there. Okay. So like at the different points, you can like find out the values here. For example, here, this is floating. So values are varying from like 20 to the 110, like that. Okay. So at any point you can find out the value and you can find out the your question was about the sorry,
U
the
plus.
u plus. Okay. 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 So what you have to do is that, for example, here in this case also. Okay. Sorry for the confusion. Okay. So draw the one line. Okay. And I'm going to make the one line on the y direction. That is going to be the a line here. Okay. So I'm going to put the line at the z is equal to, let's say, 18 meters. Okay. And y will vary from the minus, because the diameter is a 1 meter. So I'm going to draw the line from y from minus 0.5 to plus 0.5. Okay, click and draw the mesh. This line is over here. Okay. Okay, now on this line, what you have to do is that you have to draw the velocity and the y coordinate, because this will have the y coordinate only. Okay. So it should be in the direction of the y, and here you should plot the velocity. Okay. So velocity on this line. Clear? So maybe you can like change the position now on the y-axis like this. 1 minute. Velocity magnitude. Okay, like this. Clear? So once you write to the file, like here, open into the Excel. It's clear? Okay, so after that, get the data. This is like right now, my case is laminar flow. So you will not be getting the proper values of u plus or y plus. Okay, I'm just giving you the idea. Okay, so first value is my okay, first value is the velocity, second is the location. So you can say this is the velocity and this is location. Okay, y. Okay, so what you have to do is that you have to find out the friction velocity. Okay, and how you can find out the friction velocity? You have to use the this formula here. Okay, so so use this formula. So you have to find out the friction velocity, and how you can find the friction velocity at that location. So at this point, what you have to draw is that you have to put the a shear stress there. Okay, in the same simulation. Okay, so let me plot the shear stress. Okay, so what value you are seeing here on this line? There is a on the just on the wall, the value is minus 0.5. Value is minus 0.5. Wall shear stress is minus 0.5. Okay, so we are not talking about the magnitude. Okay, sorry. This is okay. Sorry. This is equal to the not. This the direction is here. This is the value is here. It's 22.4. Okay. So the wall shear stress is equal to 22.4. Okay. 22.4. And units are same as the pressure units. That is the Newton per meter square. Okay. So we have the now shear stress, and the density we have taken is equal to 1. For this case, okay, sorry, density was for this case was second. This is a laminar case, so this is not a the good case to use this data. Okay, so wall shear stress is there. Okay, so formula says that we have to use the wall shear divided by the density and a square root. Okay, so I'm going to use this value. So wall shear stress divided by the density. Okay, so the friction velocity will be equal to the square root of this value. Okay, this is the velocity units will be there like a meter per second. That's a 0.194. So you can approximate like a 0.15. Okay. So now if you want to find the U plus, this is the velocity U. So U plus will be equal to the velocity and divided by the friction velocity. So I can put the if I want to keep the value constant, this cell constant, so I can put the dollar sign in the both row and column and just drag it. So every value of the velocity will be divided by the this friction velocity. Okay. Now this is a U plus. This is a U plus right now. Okay. And similar way, from the Y plus, what I need to do is that I need to multiply and divide by the two values. So let me copy the formula. Okay. So the formula is here. If I want to get the Y plus, this is not a correct case because it's a laminar flow. Okay, you will not get the proper values or ranges. So, okay, here I'm going to multiply the Y with the what? Y with the density. Density was taken as a 1000. And I will multiply with the friction velocity, which is given here. So again, I have to keep the same value in all the rows. So I will put the dollar sign in both column and the row. Okay. And I need to divide by the viscosity. Viscosity actually was taken as a 1. So I will divide by the 1. There's no need of dividing by the 1, but you can divide it. Okay. Okay. This is how you actually end up with the because this is a laminar flow case, so you will not find the things like a proper values of the Y plus. Okay, negative value is also there. Okay, so this is how you can find out the U plus Y plus for the complete line here. This complete line, where the line is this whole line, this whole boundary layer. Okay, this line here. It's clear now. Any question? So this actually, if you want to get the actual values, and that solver will also give you the Y plus values automatically. But if you want to plot the Y plus and U plus, then you can use the Excel and just export your Y position. And Y position is like a normal to your boundary layer, normal to your wall. It can be X, Y, Z. Okay, don't worry about that. It's not a Y. The the Y is actually normal to your wall condition. Okay, that can be X, this can be Y, this can be Z. Okay. Gul Abbas, I will send you the lectures from the previous class and today's class also. Okay. Okay. So, but these formulas actually are used for giving you the initial values. For example, for estimating the first cell height, like you can find out the Y from the required y plus value, and then the friction velocity that you can find out from there. So this is starting point when you are not solving your case, because after you solve the case, you will be getting your y plus values there. Okay, but before solving the case, right now we are in the meshing phase. So how to estimate? This is the estimation method. Okay. Otherwise, once you solve the case, you can directly get the values from your CV simulation. Okay, now I am like this is a derivation of the sublayer that y because in the viscous sublayer they say that the y plus is equal to u plus, and in the logarithm layer they say this is equal to u plus is equal to the logarithm of y plus divided by k plus c. K and c are constants that we find out from the empirical, like from the experiment data, by fitting the curve on the this data, and from the curve fitting we get the constant values. This is coming from there. Okay. This is a derivation for viscous sublayer, why this equation is like this. Okay, and the second one is the equation for the logarithm layer, and why this is so. Okay, this whole derivation is given there. We applied the Prandtl mixing length formula, and we end up with these equations. Okay, and how to find out these values? Constants actually are already given from the experiments by fitting the curve on the data. And if you like, this is a regression analysis, and from regression analysis you can find out the constants of those equations. These constants are found out from there. Okay, so just put them here and you will be having the logarithm layer. Okay, and what value will be at the intersection of the both layers, viscous sublayer and the logarithm layer? This is a common point here. So for CFX, they quote the value as 11 point something, but for the fluent, they are saying the 11.225. But for CFX and fluent, they quote the different value, slightly different value. So how to find out this value? So just put the assume that the u plus is equal to this formula. Okay. So we have the a u plus. U plus will be exactly same for the both cases. So you can plus y plus here is a y plus here is equal to the logarithm formula. So compare the right hand side for the both cases, and you will this equation cannot be solved directly, or you can use some computer methods like computer numerical methods, and you can solve this equation. But by hand, it's not possible to solve. So I'm trying this because I know this value. So I just tried the value, and I found that the both sides are satisfied with this value there. Okay, one value is like at 11.06. Okay, I think CFX uses the 11.06 for the deciding about the where we are. We are the viscous sublayer or the logarithm layer, and Fluent uses 11.225, or maybe the opposite. Okay, you have to check. Okay, this may be opposite. Maybe CFX is referring to this data and Fluent to this point. Okay, but they are not like a lot of difference is there. Okay, so now I will end the class today, and we will again start the class tomorrow, but some other time. I will give you time in the group. Okay. Okay. Any questions? Any questions? Okay. Thank you for your joining.